Then they ask, well, what's the next number? How do you figure that out? Yeah, so in this case, there's a nice formula, a simple formula that fits all these numbers, right? So it's just n squared. So this is an example. These are the square numbers. It's an example of an integer sequence. So why are they called square numbers? Because they have this nice geometric significance. You take a square of size 2, it can be represented by a grid of 4 dots. A square of size 3, a grid of 9 dots, and so on. So that's why these are called square numbers. So yeah, here's an interesting thing. There's another way to think about these numbers. The nth square number is also the sum of the first n odd numbers. So like 9 is 1 plus 3 plus 5. And 16 is 1 plus 3 plus 5 plus 7. Can you see why this is true? I've kind of drawn it here. It's you just look at the square in two different ways. If you want to count the points in the square, you can do it in two different ways. One way is to just count them along rows 1, 2, 3, 4, 5, and then there are 5 rows of 5, so it's 5 taken 5 times. But another way is to count it along these lines which I have drawn. So the first line just gives a 1. The next line gives 3. Why? Because, well, so that you need to think about. The next, I mean, clearly in this picture it gives 3, and the next one gives 5, the next one gives 7, and the next one gives 9. So what's happening here is that I'm adding one new point along this row and one new point along this column each time. So totally I'm adding 2 new points along each of these L-shaped lines. So that means that I'm starting with 1, and at each stage I'm adding 2 more numbers, so I'll get the next odd number, and then I'm adding 2 more, so I'll get the next odd number, and so on. So this same pattern 1, 3, 5, 1, 4, 9, 16, we can think about it in 2 ways. We can just think of it as squares, or we can think of it as sums of odd numbers. Talking of sums of numbers, does this suggest a story? I don't know if you've heard it. It's a very well-known story. Yeah. So this person on the left is supposed to be 7-year-old Gauss. We don't know what he looked like when he was 7 years old, but this is a drawing by one of my friends. So the story is something like this. All the kids were annoying the teacher a lot. And so the teacher said, okay, I'm going to give them a problem which will keep them busy for a long time. And so the teacher said, okay, just add up all the numbers from 1 to 100. And then the students, they started writing down like maybe 1 plus 2 plus 3 plus 4 and doing it. But then Gauss, he was like immediately he gave the right answer. Okay, like with all stories, it's not clear exactly how much of this is true, but this is a nice story anyway. So how do you think Gauss did this? 50 pairs of 101. Yeah, that's one way to think about it. So here's another sequence. Let's see if you can guess what the next one is. Yeah, okay, so that's 21. How did you figure that out? What?
The common differences in arithmetic.
Ah, okay. So, so I'm adding here 2, then I'm adding 3, then I'm adding 4, and then I'm adding 5. So it's a bit like those square numbers, I was adding 1 plus 3 plus 5. Here I am adding 1 plus 2 plus 3 plus 4 plus 5. So these are called triangular numbers. Okay, why are they called triangular numbers? Well, so you can draw triangles with these numbers. So I'll just draw it over here. Is there a eraser? Well, so first you just have 1, then you have 1 plus 2, and then you have 1 plus 2 plus 3, and then 1 plus 2 plus 3 plus 4. Sort of the way they stack apples in the market, right? Except that's a 3-dimensional version of this. So these are called triangular numbers because they have that geometric sort of significance. And as some of you suggested, one way that Gauss may have, we don't know for sure, solved this problem. Well, there are many different ways of thinking about it. That, okay, I need to add 1 up to 100. Well, what I'll do is I'll do it 2 times. First time I'll write it 1 plus 2 plus 3 up to 100, and then next time I'll write it in reverse order, 100 plus 99 plus so on. Okay, but you know that when you add numbers, the order in which you add them doesn't matter. So instead of adding the first row and then adding the second row, I'll start adding the columns. And what do you see here? 1 plus 100 is 101. 2 plus 99, that's again 101. That's again 101. So it's always 101. And how many are there? 100. No, actually there are 100 here, but we are solving the wrong problem. We are adding it up twice. So we get 100 into 101 divided by 2 because we did it twice, right? So 2 into our sum is 100 into 101, and so our sum is 100 into 101 by 2, and if you are good at calculating, you can see that it's 5050. Okay. So here's another series. So how do you figure that? So the pattern here is that each term in the series is the sum of the previous 2 terms, right? So yeah, this is 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13. So the next one should be 8 plus 13, which is 21. And after that, you can see what it should be. So these are called the Fibonacci numbers. And if you want to write a formula, you say the A0 is 0. Well, this is the 0th term. Then you take 1. You can also start with 1 and 1. And then each term is the previous term plus the one even before that. So you just keep adding the last 2 of the numbers that you've written until now. And it has an amazing formula actually, the nth Fibonacci number. So if you want to calculate the 1000th Fibonacci number, by the, normally you would think that, okay, I'll have to start with 0 and 1 and then do 1000 steps to calculate the 1000th Fibonacci number. But that's not true. There's a very nice formula which is kind of amazing because you wouldn't expect this horrible thing with root 5 minus root 5 and divided by root 5 and so on to be an integer, right? It looks like it may be something complicated. I don't know, you may have solved quadratic equations in school, and then you would have seen that if you take these kinds of square roots and add and multiply them, you don't usually get integers unless you're very lucky. So when your teacher asks you to simplify this with n equals, you can give these to your teacher, you can put n equals 3 here and ask him to simplify it, right? And you can immediately, you could do it for n equals 10, you can give this to your teacher, and you would be able to do it in 10 steps. Of course, for small n, this is easier to do using the Fibonacci, the fact that it's a Fibonacci sequence, but it's difficult to do by hand. But a computer can do this quite easily. Anyway, so at least get a good approximation. And this number which appears here, it's called the golden ratio. So it's attributed a lot of magical, mystical properties and so on. It's like it's the ratio of the length to breadth of an A4 sheet, but A4 sheet, yeah. So I don't know, I don't understand why, but artists say that this is a very pleasing proportion. So, you know, a square is too boring, and this is somehow nice. If you actually ask how fast do these Fibonacci numbers grow, they grow very fast. I have here some, let's see. So I use this software called Sage, and it has lots of nice things. So I can say Fibonacci sequence of, how big should I go? 1 million. Uh-oh. Yeah, so let's do it like this. 1 million. Yeah, actually let's just do, let's see, Fibonacci, 1 million. Did I put the right number of zeros? Too many zeros. That's kind of slow. Let's try 1 million like you said. 1, 2, 3, yeah. Whoa, okay. So, right. It's there somewhere. I'm still scrolling up. Hang on, it's there. All right, I give up. So there's a way to do this. I'll say length of the string that I just got. All right. So that number, Fibonacci of 1 million had 200, what? 2,08,988 digits. Okay. The general pattern here is going to be that if you take the if you take the 10 millionth Fibonacci number, the number of digits will roughly be 10 million divided by 5. If you take the 10 gazillionth Fibonacci number, the number of digits will be roughly 10 gazillion by 10 to the power 5. So this is a phenomenon which is called exponential growth. Every time you increase your parameter by a constant amount, your number actually scales by a certain amount. So what's happening here is that the nth Fibonacci number grows like this number to the power n. And if you study your logs and so on, you will be able to try, I mean, I don't know, some of you may be preparing for IIT and things like that. You can try to see, try to convince yourself of what I just said, that if you just assume that the nth Fibonacci number grows like this, then roughly the number of digits when you take the nth Fibonacci number will be n divided by 5. Okay, here's a simpler example. Just take the sequence 1, 10, 100, 1000, 10,000. So the number of digits of the nth number in the sequence is just n, right? Or yeah, it's just n. So this one is n by 5. So it grows slower than that, but it still grows pretty fast. This fast growth of the Fibonacci number is actually very useful for us. How many of you have seen the GCD? Do you know the GCD of two numbers? HCF, the highest common factor, right? So how do you calculate the highest common factor of two numbers? Okay, so I'm hearing two answers here. So when you're in 6th standard or something, you learn to do it by prime factorization. So you take the, say you want to find the GCD of 12 and 8, then you write, okay, 12 is 2 to the power 2 into 3, 8 is 2 to the power 3. So I'll look at the common prime factors in both of them and multiply them out, right? That's a nice approach. It's easy to understand, but it's not the fastest. The fastest is Euclid's algorithm. So Euclid was a mathematician in ancient Greece, and he had this beautiful algorithm for computing the GCD, which is still used in all your phones and computers for various reasons. Okay, so Euclid's algorithm is still current state of art. So let's just recall how you use Euclid's algorithm. So Euclid's algorithm works something like this. You're given two numbers, say let's do 12 and 8. And what you do is you take the smaller number and divide it into the larger number. Okay, so 8 goes into 12 once, and the remainder is 4. Okay, the principle is this: you just replace the larger number by the remainder. And now 4 goes into 8 two times, and the remainder is 0. So we'll get 0 and 4. Once you get 0, you just look at the other number, and that's going to be the GCD. Let me show you another example. So let's do the thing of 13 and 21, okay? I know that. Let's just go through the algorithm. So there's a reason I picked 13 and 21. You notice that they are Fibonacci numbers. So when you try to do it with 13 and 21, the 13 goes into 21 once, and the remainder is 8. Okay, and 8 goes into 13 once, and the remainder is 5. You see what's happening here? I'm getting Fibonacci numbers at each stage, and this is taking very long. I mean, when I did 12 and 8, it only took 3 steps, and this is just slightly larger numbers, 13 and 21. It took 1, 2, 3, 4, 5, 6 steps. Right, so it took 6 steps to find the by Euclid's algorithm to find the GCD of 12 and 31. So this is sort of a worst case scenario. So Fibonacci numbers give the worst case scenario for the GCD of an algorithm. So again, you can, if you want to set up a GCD problem which takes the most number of steps for the smallest possible numbers, just choose 2 Fibonacci numbers which are next to each other in the Fibonacci sequence. And you'll have a lot of steps because you'll just go through all the Fibonacci numbers. And what I'm saying is that any numbers of the size 21 and 13, it will definitely be done in 5 steps. So this is the worst case scenario. So because Fibonacci numbers grow really fast, this means that Euclid's algorithm actually for very big numbers you can do in very few steps. So if you have numbers with roughly n digits, or say if you have 2 numbers with 1000 digits, then you will be able to do their GCD with Euclid's algorithm. Worst case scenario so I think it's, so if you have the nth Fibonacci number, that GCD can be formed in n steps. And so if the nth Fibonacci number is roughly, n by 5 digits, right? So if you have numbers of n by 5 digits, you can find the, so you have numbers of 2000 digits. These are astronomically huge numbers, which, it's many orders of magnitude larger than the number of atoms in the universe. But you can still, in a few thousand steps, which a computer can easily handle, run Euclid's algorithm for them. So this is a fact that ensures that the RSA public key crypto system, for example, which we use for all our internet security and so on, works in real time. So you see, this very innocuous study of Fibonacci numbers is what we use all the time in. Okay, so here's a interesting observation. No scientific discovery is named after its original discoverer. It's called Stigler's law of eponymy, and it means that names are always, so another variant of this that I've heard is that everything is named after the last person to discover it. People keep discovering things, and then it's named after someone, and then you no longer can discover it. This is Actually, Stigler's law was a scientific discovery of Robert K. Merton. Okay, and so it is also with Fibonacci numbers. So Fibonacci numbers are named after this gentleman, Leonardo Pisano, who was from a very distinguished family in the city-state of Pisa in what is now Italy, the Bonacci family. And Fibonacci literally means a son of the Bonacci family. Okay, and his father was posted in northern Africa in a place which is now in Algeria as an official for the city-state of Pisa. He looked after the business interests of Pisa in Algeria. And there were a lot of these, there was influence from Persia, which then had influences from India. And there Fibonacci learned the Hindu-Arabic decimal number system. And he introduced this system to Europe in his book called Liber Abaci. Liber Abaci is just Latin for the book of calculation. And well, it's an amazing thing that he did, but unfortunately, or for whatever, he's remembered for a rather silly example in that book about reproducing rabbits. And I won't go into this. Maybe you know this already. He had a lot of colorful rabbits which reproduced, and he counted them and so on. But here's an actual page from one of the original manuscripts, and you can see here this our modern numerals appearing. Slightly, 5 looks slightly different, maybe 3 looks slightly different. So he introduced the place value system, the numerals 1, 2, 3, 4, and so on to Europe in the 12th century. And in that book also, here you can see Fibonacci numbers 1, 2, 3, 5, 8, 13, 21. So it's all in there. And this is what he's somehow remembered for, despite his huge contributions to European mathematics. But Fibonacci numbers are very old, and in India somehow a lot of mathematics it wasn't a separate subject. It was integrated with a lot of other things. And we have the Indian scholar Virahanka around 6th century. So this would be 600 years before Fibonacci. And he was studying poetry. I don't know, how many of you learned shlokas? Yeah, so in shlokas, you know that in Sanskrit you have short vowels and long vowels. I. I guess you have them in Tamil too, but the thing about Sanskrit is that these shlokas are written with a very strict meter, that the length of the thing has to be exactly a certain number of beats. And one way of counting these beats is to say that each short letter is 1, like is 1, but is 2. I is 1, but E is 2, and so on. And so you can think of a meter as just a string of 1s and 2s. How many short vowels and how many long vowels? Ignore the consonants. Then the total number of beats is just the sum of the numbers in it. So if you are looking at shlokas with just 4 beats, then they could be all short, right? 1, 1, 1, 1, or 1, 1, 2, or 1, 2, 1, or 2, 1, 1, or 2, 2. Okay, so these are the different patterns that you can have with long and short beats. And you can ask yourself, well, how many different patterns are there with n beats? And this is what Virahanka was looking at. And so what he observed was that if you want something with n beats, say you want something with 10 beats, then you can take something with 9 beats and add a short beat to it. Or you can take something with 8 beats and add a long beat to it, right? And in this way, you will get all things with 10 beats. Everything with 10 beats, you look at its last thing, it should either be short or long. You remove that, you'll either get something of 9 beats or something of 8 beats. So basically, this is a way of generating all these things, and what you get is the number of patterns with n beats is the number of patterns with n minus 1 beats plus the number of patterns with n minus 2 beats. Yeah, it's a Fibonacci number. So do you see what I'm saying? With 10 beats, well, you can get it by adding 1 to something with 9 beats. So you'll get, exactly the number of patterns with 9 beats plus the number of patterns with 8 beats, because you can add a long beat to something like that. And you can actually represent these as a graph. So those red lines are just adding 1 beat, and the blue lines are adding 2. No, they're not quite. They're sort of reflecting. So this, let me just show you this. So this 2, 2 is adding a 2 to this. Okay, so this 1, 1, 1, 2 is adding a 2 to 1, 1. So you're going down 2 levels and sort of this. All right, so, oh, what's this? All right, I'm not sure what this is, I forgot. Luckily, I can look it up. This, have you seen this? How many of you have seen this? So you've heard of encyclopedias, right? Like Wikipedia or I don't know, when I was small, we used to all have Encyclopedia Britannica, stuff like that. So this is the online encyclopedia of integer sequences. It's more like a dictionary. Each entry in this dictionary is just a sequence of integers. And what was my sequence I had which I forgot? 1, 2, 6, I didn't hear you. 24, 60, I didn't hear you. Anyway, I'm still going to look it up. Well, look, it occurs in here. So it's part of this sequence. Well, there's a lot of sequences where it appears. Here you go. Maybe the next term should be 208. Why not? Maybe the next term should be 180. Well, so this encyclopedia has all possible sequences which start or contain the terms 1, 2, 6, 24, 60. Okay, so I don't remember how I came up with it, but there are many possibilities here. There are about 10. So let's put, but suppose I put the next one. What do you want to put? 360. $240. Okay, so it's not in there, but these are the factorial numbers. This grows very fast. It grows faster than the Fibonacci numbers. And there are, you can estimate its rate of growth and so on. What about this? Whoops. Prime numbers. So the next one is 13, right? And can you give me a formula for the, what is the 100th prime number? So I have a computer program for that. You want the 100th prime number? It's 547. Anyway, so how fast do these things grow? So this is actually a very interesting problem in mathematics. These prime numbers, you can start writing them down, calculating the next prime number and so on. And it's very mysterious how they grow. There's no formula that we know, no simple formula. I cannot write like it's, like the Fibonacci numbers. I can't write down a recurrence relation. I can't write down a simple formula for the nth prime number. And so it's been something that, over many centuries mathematicians have studied. Anyone recognize these people? Ramanujan over there from Namma, Chennai. That's Euler. That's you saw him earlier adding up numbers, Gauss, and that's Riemann. Yeah, it's a German name, so it's pronounced Riemann. So, and around 1896, people figured out how fast these grow. It was so I think Gauss already kind of predicted how fast they should grow, and it was a theorem that was proved by de la Vallée-Poussin in 1896. So he said that the nth prime number is roughly as large as n log n. This is log to the base e. Let me show you an example. Ln, yes, ln. So for example, the 10 to the power 7th or 8th thing is this number, and if you compute the log, it's like this 16 whatever, but 0.509. So they're at least they're the same order of magnitude. Okay, if you plot the graph, you'll see that this is the nth prime number, and this is n log n. So they seem to be diverging a bit, but they grow pretty much at the same rate. This remains to this day a very interesting research problem in mathematics, trying to understand exactly where to find the next prime number. So we know roughly how big it will be, but to pinpoint this thing, and I had Riemann's name there. I don't know if you've heard of the Riemann hypothesis. So there's this thing called the Riemann zeta function, and this is the puppeteer that controls the prime numbers. And if the Riemann hypothesis is a very subtle statement about this Riemann zeta function, using which you can predict when the next prime number will happen. Okay, so with this I'll stop. I'll just mention that this. How many of you program? Okay, so program. So nowadays, it's really very accessible. There's a lot of easy to use and nice software. And what I'm using here is called Sage. So you can use this to do calculus. You can use this to do trigonometry. Oh, looks like the internet connection. Oh, yeah. You can use it to do linear algebra. There are lots of books you can use to explore mathematics using Sage. So some of them are actually, there are not many which are at the school level, but there are a couple here which are at the school level also. So, right. So with that, I'll stop here. I hope this talk will. I mean, I can't tell you much in half an hour, but I hope this talk will motivate you to go home and explore yourself these sequences and use the online encyclopedia and use Sage, and you have at your fingertips such powerful tools nowadays. Everybody can become a mathematician. Thank you. Questions? Yeah. Yeah, I have a few minutes for questions if you have any. Oh, yeah. Do you have a mic?
Just a common fallacy in the sequence including the factorial numbers. How is 60 coming there? Shouldn't it be 120?
It should be 120, is it? Ah, that's why it didn't match. So let's go back and see. Factorial numbers, the very first hit. Good. I was wondering what's going on there. Thanks. So yeah, it's the power of suggestion, right? I put the wrong thing and everybody still guessed the next number would be 360. Good, thanks for clearing that up. It was bothering me. Any other questions? Don't feel shy. Yeah. Examples? There's only one golden ratio. Sorry? What do you, I mean, there's a golden ratio, it's a number. How can I give you more examples of it? Where it occurs in real life? Yeah, so, everywhere? He says everywhere. I don't really actually.
Snails, sunflowers.
Really? Okay. I see. I'm kind of not. I don't understand this real life business. So maybe your friends know more about real life.
Sir, I just know what, sir, it is the ratio of the male bees to the female bees in a beehive. That's the only one I know.
Ratio of the length?
Ratio of the male bees
Oh, the number of male bees to the female. That's very interesting. So.
in a beehive. So I got only one example I'm asking you.
Yeah. So I'll tell you where a lot of things about this come from. So it's this number comes from a quadratic equation, right? So we're saying that the nth Fibonacci number is n minus 1 plus n minus 2. Now suppose this Fibonacci number grows at a certain ratio. So suppose it's not true, but suppose we say that this is something to the power n, x to the power n, then this x to the power n would be x to the power n minus 1 plus x to the power n minus 2, right? So if you write the difference here, this should be 0. Don't ask me, and so I can write this as x squared minus x minus 1 equals 0, and here I have x to the power n minus 2. But this I don't need to worry, well, x equals 0, but this has two solutions, and that's root 5 plus 1 by 2 and root 5 minus 1 by 2. And those are the two numbers which appear in the thing for the Fibonacci sequence. Oh yeah, it's somewhere here, right? It's on my T-shirt. Varuni will explain it. Huh? Oh, I'm not sure. Okay. Oh yeah, these things. So if you look at these volunteers' T-shirts, there are these things called Penrose tiles. So there are two kinds of tiles. There are darts and there are kites. And these tiles have the nice feature that there are two lengths of sides. One of them, the longer side and the shorter side. They have a lot of magical properties. They're called Penrose tiles. So one of the amazing things about this T-shirt, did they get anything with these tiles? It's on the poster. It's also on the books that you have. No? No, it's not. Okay. So these are called Penrose tilings, and these have an amazing property that you start tiling a floor with these tiles. Okay, they fit together. It's very tight. There's only a certain ways in which you can extend the pattern. Once you start a pattern, there's only one way in which you can extend it. And so you can, but the amazing thing is that you can keep extending it indefinitely until you have tiled the entire, as large as you like. So, and then the other amazing property about these tiles, well, you could do that with square tiles too, so what's the big deal? But the other amazing thing about this tile is that the pattern that you'll get, the tiling pattern that you'll get, will never repeat itself. With square tiles, every place looks like every other place, but with Penrose tiles, it never repeats itself. And one thing about these Penrose tiles, they have to be, so they are very special. And amazingly, the ratio of the longer side to the shorter side in these tiles is the Fibonacci numbers. I'll encourage you to read an article by Martin Gardner. He used to write in the American Mathematical Monthly, but you'll find, I don't remember which book it is, but he has an article on, well, you're all, I'm sure, very good at using the internet. So Martin Gardner has an article on Penrose tilings. But you can even just look for Penrose tiles. There's lots of nice resources on the internet on this. All right, are we? Oh yeah, there's a question in the last row. Oh yeah, so I think we need to have a talk about the. I think you should read what's written, and there's some fine print over there. Huh? Okay, so there's a fine print there. Usually fine print says that, you know, everything you have belongs to us and so on, but in this case it actually explains the ants. So. All right, so any